Okay, so we are in the process of calculating the moments of a general normal distribution from the moment generating function for a general normal distribution. But before we did that, we decided to have a bit of a recap of standardization of a general normal distribution. So we've gotten to this statement here that p double prime of this event that z is less than or equal to some little z, this event here in this space, must be equal to p prime of the corresponding event here in this space. And we know that this is the CDF for this distribution up here. So if we turn over, if we get some more paper rather, if we get some more paper, this is the equation we've got so far, that p double prime, that z is less than or equal to little z, should be equal to p prime, that x is less than or equal to sigma z plus mu. But this is equal to the CDF of that original random variable x evaluated at sigma z plus mu. And we know that that is equal to the integral from negative infinity to this value, sigma z plus mu, of the PDF of the general normal distribution. So I'll just write little f of big X evaluated at some little x dx, basically. If we integrate that, so basically what I'm saying is if we want the CDF evaluated at this value, we just integrate the PDF from negative infinity to that value. And the PDF of the general normal distribution, so if x is distributed normally with mean mu and variance sigma squared, we know that the PDF is equal to 1 divided by sigma the square root of 2 pi e to the negative x minus mu over sigma squared divided by 2. Okay, so now we can stick this into this formula and we'll get that it's equal to the integral from negative infinity to sigma z plus mu of 1 divided by sigma the square root of 2 pi, that should be, e to the negative x minus mu over sigma squared divided by 2 dx. So just do a u substitution. Let u equal x minus mu over sigma. So firstly, let's adapt the limits. If we adapt this limit, if we put in this limit into here, then u is going to equal sigma z plus mu minus mu over sigma, which is just going to equal z. So the upper limit goes to z. If you put in negative infinity to there, it remains at negative infinity. Okay, the other thing we're going to have to do is we're going to have to change dx. So we replace it, du is equal to dx divided by sigma. So dx is equal to sigma du. So now if we substitute all of those things in, we get that this integral is equal to the integral from negative infinity to z. So I've replaced this upper limit with z. And then I get 1 over sigma the square root of 2 pi e to the negative, the whole point of defining it like that was so that I could replace this with u squared over 2. Then if I replace dx with sigma du, I get sigma du in there. And then I get the integral from negative infinity to z. The sigma here cancels with the sigma here, so I get 1 over the square root of 2 pi e to the negative u squared over 2 du, but you will notice that that is just the PDF of a standard normal distribution integrated from negative infinity to z, which is just the CDF of a standard normal distribution, i.e. it's this phi function of z. So we get, if we go right the way back up here, that the p double prime of the event that z, big Z, the random variable big Z, is less than or equal to z. So p double prime, that z is less than or equal to z, which we could have written as the CDF of big Z evaluated at z is equal to phi of z, which implies that big Z is normally distributed with mean 0 and variance 1. So that is why you can standardize general normal distributions. So if you have a general normal distribution here, which is big X, then you can always find a transformation, namely this transformation here, which will map it onto, and if when you compose these two together, you'll get another random variable, which will be standard normally distributed. Okay, so we know that the moment generating function, we calculated in the previous video that the moment generating function as a function of t for a big random variable z, which is normally distributed with mean 0 and variance 1, is equal to e to the t squared over 2. So what we can now do is let's calculate the moments for this. We want to calculate the moments for from our moment generating function. So we recall that the moment generating functions could be expanded as the expected value of x to the r times t to the r over r factorial of summed from r is equal to 0 to infinity. So it's this infinite series, and we note that how similar this is to the Taylor series. We noted how similar this is to the Taylor series, and this therefore means that the rth derivative of this moment generating function is equal to the rth moment of our random variable x. Okay, in this case it should have been the random variable z rather than x, since our random variable here was z. Okay, if you wish, you could attempt to differentiate this r times. It's going to be messy, but there's a much cleverer way of thinking about this, because if you remember, the Taylor series of e to the x is equal to the sum r is equal to 0 to infinity of x to the r over r factorial, and that is valid for all x as an element of the real line. It's actually valid for all x as an element of the complex plane, but it's certainly valid for all real numbers. So t squared divided by 2 is a real number. Whatever it is, t is some real number, so when you square it you get some real number, and when you divide it by 2 you get some real number. So t squared over 2 is a real number. Therefore, if I want e to the t squared over 2, I can view this as the summation r is equal to 0 to infinity of t squared over 2 to the r over r factorial, and that is far more sensible than trying to view this as a function of t and trying to work out the Taylor series from scratch. It's far simpler just to work out the Taylor series for e to the x and then substitute t squared over 2 into there. Okay, if we finish this off, if we just expand this, we get the summation from r is equal to 0 to infinity of t to the 2r over 2r times r factorial. So if we write a few of these terms out, we'll get 1 as the first term. When r is equal to 0, we'll get a 1 here. Anything to the power of 0 is 1 over 0 factorial, which is 1. Then when r is equal to 1, it's easier actually to work with it over here. When r is equal to 1, you'll get t squared over 2 over 1 factorial, which will give you plus t squared over 2. Then you'll get, when r is equal to 2, you'll get t to the 4 over 4 over 2 factorial, so you'll get t to the 4 over 8, and it goes on. So you only get the even powers here is important. Okay, so if we turn over, so if we know that our moment generating function for the standard normal distribution is equal to the sum r is equal to 0 to infinity of t to the 2r over 2 to the power of r times r factorial. Now we want it in the form the sum r is equal to 0 to infinity of t to the r over r factorial times the expected value of z to the r. So there's something wrong here, because this has only got, this is counting up the even terms, this is adding up even terms, this is adding up all of the terms. So that instantly gives us that if you've got an odd term over here, so if we remember this is 1 plus t squared over 2 plus, what was the next one, t to the 4 over 8, was it? Then on this side we've got 1 plus t times the expected value of z plus t squared, the expected value of z squared over 2 factorial, etc. So we can instantly say that all the odd moments are equal to 0. So e to the z n, where n is an odd number, n is odd, has to be equal to 0, because on this side we don't have any odd powers of t. The other problem is that in this sum here, we are dividing by r factorial rather than 2r factorial. This should be, you have t to the power of 2r, so if you get the corresponding term over here, so if you look over here, t squared, this has been divided by 2 factorial. In this case, it was divided by, in this case where we had r is equal to 1, okay, start again. In this side, when you had the term t to the power of 2, you divided it by 2 factorial. On this side, the term t to the power of 2 came when r was equal to 1, therefore was divided by 1 factorial. That's not good, because we need it divided by the same value factorial as you have the power. So we need to rewrite this. The moment generating function of z as a function of t is equal to the sum, r is equal to 0 to infinity, of t to the 2r over 2r factorial, and then what we have to do is make it correct, so we have to multiply the top by 2r factorial. We'll get r factorial 2 to the r there. Okay, so now this is correct, and this term here, this must equal the expected value of z to the power of 2r, basically. So, if you give me an even number, if you give me an even power, basically, so if you give me e to the zn, where n is an even number, is even, then it's equal to n factorial divided by n over 2 factorial divided by 2, times by 2 to the power of n over 2, basically, is how you compute the even moments for the standard normal distribution. Got there in the end. Right, so if you remember, we started off originally though with asking the question of what are the moments of the general normal distribution. So this one back here. So we know that x is equal to, well, t inverse of z, but t inverse is equal to the function sigma z plus mu, i.e. the inverse function of that. So we can view this as overall being sigma times z plus mu. Okay, so that's how we would transform this this new random variable which we constructed z, which was standard normally distributed, how we transform it back into our general normal distribution, which was our original problem. And you might have said, well, we already had the MGF of this general normal distribution. Why didn't we just, do this for the general normal distribution? And you could have, but we are doing it for the practice of standardization of the normal distribution as well, which is actually far harder than just, just doing a bit of calculus to calculate the moments. Okay, so x is equal to sigma z plus mu. So now, if we want the expected value of x to the n, x to the n, yes, we can view this as the expected value of sigma z plus mu to the power of n, and you could think of this as